Hello everyone, welcome back to the channel. We are doing lead code 2787 ways to express an integer as a sum of powers, and it's a very interesting question. So let's see what the problem statement says. It says you're given two positive integers n. So this is the first thing that you're given, and then you're given x. Let's see what we have to do with those n and x. Return the number of ways n. So this particular number can be expressed as the sum of the xth power. So for example, if x is given as 3, so we are saying that to the power 3, something to the power 3, expressed as the sum of the xth power of unique positive integers. Now, this unique word is actually very important over here. Unique, right? And I'll tell you why it's important. In other words, you need to find the number of unique integers where n1 to the power x. So basically n1 to the power 3, n2 to the power 3, so on and so forth. If you sum all of these numbers up, you should be able to make up the original n, which is this. All right. Now, in the end, you are expected to return the number of ways, not the exact ways, the number of ways. All right. Now, the result can be very large, return it modulo, and then they have given us this, this particular line as a, you can say, as a further explanation that if, for example, you're given n is 160, x is equals to 3, then one possible way to make 160 with powers of 3 is that you take 2 to the power 3, which is 8, you take 27, and you take 125. If you add all of these numbers up, you get 160, right? So the first thing when I look at this question, when I read the problem statement, is that okay, let's take all the integers that I have and calculate what their power is. So for example, 1 to the power 3, 2 to the power 3, 3 to the power 3, so on and so forth. Let's list all of them, and then at a certain point you're going to realize that this and all the numbers after this are out of the question. Why? Because 6 to the power 3 is actually bigger than what we are trying to make in the first place, right? So you don't need to consider any of these numbers. What you have to work with are the first three things. So what your possible solution set is this. Okay, so from this, if you take 125, do not take 64, take 27, take this, and do not take this one. So you take some of them and you do not take some of them, you get the overall final answer. Now, why did I emphasize on the word unique? What they are saying is return the number of ways uh, in which you can, sort of take unique positive integers, put them to the power x, and make up n. Now, for example, let's say that x was equals to, let's say 2. Okay, x was equals to 2, and then n was equals to, let's say, 32. Now, you know for a fact that if I do 4 square plus 4 square, that is 16 plus 16, and that's equals to 32. But then this won't be considered a correct you can say a correct answer for this particular problem. Why? Because we are searching for unique positive integers. Okay, so this problem is actually easier. If this word wasn't there, then I would have also had to take care of this case, but right now I don't have to worry about it, and you know what the reason for that is. All right, so let's have a look at these two example test cases that we are given. So n is equals to 10 and x is equals to 2. So I'm going to do the exact same thing. I'm going to list all the possibilities. Okay, without even thinking, I'm going to list all the possibilities because that seems to me like the easiest way to solve this problem. So what is 1 to the power 2? What is 2 to the power 2? What is 3 to the power 2? What is 4 to the power 2? So on and so forth. So this is 1, this is 4, this is 9, and this is clearly out of the picture because this is 16, which is bigger than 10, right? Now, what way do I see in order to make 10? 1 plus 9. 1 to the power 2 plus 3 to the power 2. And this is the only way in which I can make this, and no other possible way, no other possible, you can say, method is possible, right? So n is equals to 4. What I'm trying to make is 4, and the power is 1. So 1 to the power 1, 2, 3, 4, and 5 is actually out of the question. right? 5 and all the numbers which are bigger than 5 are out of the question. Now I can see 1 plus 3 is 4. This is one possibility. And then this 4 in itself is another possibility. So that is why the answer for this test case is 2. Now, what I want you to do is pause for a moment over here and think of how we can implement this exact same approach inside of our coding environment. So this was basically, we were talking about, up and until now we were talking about how the you can say the overall bird's eye view is going to be. But then how do I actually implement this take and not take approach? By the way, does take and skip, does this ring any bells? This is nothing but recursion, right? This is nothing but recursion. And then whenever we are doing recursion, we see if we would be able to memoize or not. If it, if for example, the take and skip, if it follows a certain pattern, if there is, what do we call that, repeated problems, I don't exactly know what the technical term for that is, but then if in simple words, if you have two or more states which are repeating, so if you have one certain state which is repeating more than one time, then I can very clearly memorize it, I can very clearly cache it, right? So how am I going to exactly implement this take and skip approach? Let's see that now. Okay, so what I have to do is, let's say n is equals to 160 and x was equals to 3, right? So 160 is basically what I'm trying to make. And I know for a fact, I know 100% for a fact that I am worried about unique positive integers, right? So what I will do is this thing, keeping in mind that I have to take some of those possibilities, I do not have to take some of those possibilities. What I'll say is, okay, let's do one thing, let's try to subtract 1 to the power 3 from it, from 160, so the resulting number is going to become 159. But then if you think about it, we did not actually have to take 1 to the power 3 in order to make 160, right? What I had to do was I had to skip it. I do not have to take 1 to the power 3. Now, okay, let's say I skip it. Then I again have two choices for 2 to the power 3, which is 8. So if at this point I have 160, right? And if I take 2 to the power 3, the resulting number becomes 152. So what I'm drawing in front of you is the happy path. Okay, the happy path is basically the path which gives you the answer, which gives us one of the answers in this case, because there can be multiple happy paths, right? I'm not going to draw the overall entire tree structure in front of you because it's going to consume a lot of space. I'm just going to draw the happy path for you. And in this scenario, the answer is 1. So if you have 160 as your n and then you have x as 3, there's just going to be one path, which is, so there's just this one possibility that you can make 160. You don't have multiple possibilities, right? So over here, what you can do is you can also not take 2 to the power 3. All right. Now it comes to 3 to the power 3, whether or not you want to take it. So if 3 to the power 3 is what, 927, it's 27. If I subtract 27 from 152, what do I get? Let's see. 152, 27, this becomes 4, this becomes 12, 5, 2, 1, right? 125, obviously. Now I have 125 remaining, and I also had a possibility to skip 3 to the power 3. Now what I'm going to do is I'm going to say, okay, should I or should I not take 4 to the power 3, which is equivalent to 64. What I'm going to do is I actually am not going to take 4 to the power 3. So I'm going to skip it. All right, sure. Now, since I skip it, I have 125 remaining because I did not subtract 64 from 125, right? What I'm doing is I'm skipping. I'm saying that, okay, skip it. Over here, I have 5 to the power 3, which is equals to 125. And then when you do 125 minus 125, you get a 0. As soon as you get a 0, you know that the path which you have drawn, is 101% correct. So what I'm going to do is I'm going to return 1 from here. Now what does this 1 indicate? This 1 indicates that okay, you have successfully found one happy path. All right, and then for example, if I had skipped it, I could have skipped it. I could have skipped 5 to the power 3. When I think about taking 6 to the power 3, that number in itself is actually bigger than what I'm trying to make. So from such a case, I'm going to return 0. That I'm going to say that okay, if I take this particular path, I'm sorry, but I am not able to find any happy paths if I follow this path, right? And since this number is in itself bigger than what we are trying to make, do you think that we need to explore the not take path? We do not even try to explore this path, because if taking this number doesn't help you, skipping it is also neither going to help you, right? Because this is it in itself bigger than what we are trying to make. So 7 to the power 3, 8 to the power 3, they are obviously, very obviously, out of the picture. So this is exactly what I want to code up, right? So let's see if I put it over here, and let me actually open up lead code as well on the other side. Right, so here it is. I'm given integer n, integer x, and now I have to implement this exact same thing that we're talking about. So what we are going to do is we are going to make a function which is solve, and now I need to worry about what do I need to pass to that function. So I need to pass to that function, first of all, what the value of the number is that I'm trying to make, and I also need to send the power x. And what else do I need to send? I need to send what my starting number is. My starting number is obviously 1, right? And what I'm going to do is, in the subsequent recursive calls that I'm going to make, I'm going to increase this particular number. All right, I'm going to increase this particular number from 1, then 2, then 3, so on and so forth. So 1. Now let's see. I have integer solve, I am receiving n, I am receiving x, and I am receiving the current number, what the current number is. All right. Now, as soon as I receive the current number, what do I do? First of all, I calculate what the what the actual value is. So 1 to the power 3, or 2 to the power 3, or 3 to the power 3. So what I'm going to do is calculate the value. How? I'm just going to simply say the current number, which is 1 to the power x, because x is actually 3, right? Current to the power x. That way I have calculated the value. Now what do I need to do? I have two decisions, and one of those decisions is going to ultimately end up in a happy path. So the first this decision is take, right? And take is, it's going to be equals to what? It's going to be solve, then n is what I am trying to make, minus the value. Because when I'm taking something, as you can observe over here, when I take something, I subtract the subsequent value from n. So for the next recursive call, just like over here, you see, I skipped the 1, right? But I did take the 2. So what did I do? My n was 160, but for the next recursive call, I had 152. So I subtracted 2 to the power 3 from 160. That's exactly what I'm doing over here, n minus value. And since I'm recursively calling the function, the power is going to, no, the power is actually going to remain the same, and current is going to increment, yeah, 100%, because this is current, right? This is current. In the next power, this becomes 2, then it becomes 3, so on and so forth, 100%, right? Similarly, int skip is going to be, you don't have to take the value, whatever value was you don't have to take it. Like over here, I did not take the 1, right? X as it is, and current plus 1. And what you have to do is just return the happy paths which you get from skip, and the number of happy paths which you get from take. Now they said that you have to return the modulo, right? Since the answer can be very large, you have to return it modulo 1e to the power 9 plus 7. So I'm going to take care of that as well. I'm going to say, okay, you don't have to return skip plus take, you have to return it modulo m. Perfect. And what we are, what's just left is are the base cases, right? So if at the end of the day you get an exact zero, if at the end of the day you get an exact zero, you return a 1. If you get any number which is less than 0, you return a 0. So what I'm going to say is, okay, if n, because we are doing n minus value, right? If n is equals to 0, you return a 1. If n is less than 0, if it's become negative, then you return a 0. You say that from this particular path, I won't be able to get any, you can say, any happy path. Now we also said one thing, that if the value has exceeded what you are trying to make, what I'm trying to make is 160, but then 6 to the power 3 is 216, then do not do anything, just return from there, because that sort of lets you know that now your recursive call, now there are no more recursive calls which are needed. So I'm going to say, okay, if value, if it has become greater than what I'm trying to make in the first place, if value has become greater than what I'm trying to make in the first place, just return 0. No more happy paths to be taken from there. Now if I run this code, let's see if it passes the example test cases that we have. It does. But then if you take a look at the constraints say that n can be up to 300, x can be up to 5, and n can be up to 300. So if I just submit the brute force recursion, it's 100% going to give me a time limit exceeded error, right? Let's see. It gives us a TLE, and it only passes around one third of the overall test cases, right? It only passes one third of the test cases. So let's see how I can uh, memoize it. And we'll also talk about why is memoization possible in this case, right? So n can be at max up to 300, and then x at maximum it's going to have a value of 5, right? So okay, what I'm going to do is I'm going to make an array dp, and the variables which are changing, first of all, n is changing, n can at maximum be up to 300, so I'm going to say 301, because the maximum, the largest value of n can be 300. So in order to store that, and the next thing which is changing is actually x, and sorry, the next thing which is changing is current. So basically 1, 2, 3, so on and so forth. And if you think about it, the maximum value which current can go up to is also 300. Why? Because if I need to make 300 and x is given to me as 1, then the one of the answers for that would be 300, would be 300 to the power, sorry, current, I'm sorry, current to the power, what's happening, what's wrong. So what I'm saying is, in that scenario, current to the power x, so current will be equals to 300 and the power will be equals to 1, right? So this I also need to make sure that this is 301, because at maximum current can also go up to 300. What I'm going to do is, first of all, say that, okay, fill up the dp array with -1. So mem set dp -1 size of dp, fill the entire 2D array with -1. So all of the values are -1s, and then I'm going to say that cache all of the results. So if you have calculated successfully the value of one state, cache it. So dp of n x, sorry, not x, dp of n and current will be equals to this. And also if you already have the value for that state, just return it simply, dp of n current. If it's not equals to -1, then that means that you have already, in the previous iterations you have already calculated that value. So just return dp of n comma current, right? That is it. Now if I submit this code, it should pass all the test cases, hopefully, right? Let's see. Why does it not? Because percent mod m index 301 is out of bounds. So index 301 out of bounds. Why am I going to 301? No, dp of n comma current. If I do this 302, would it now pass all the test cases? Yeah, it does. So we are passing all the test cases that we have. And now if you think about the time and space complexity, let's see how much time we are taking and how much space we are taking. All right. So in this case, we observe that there are two decisions that we are making at each and every space. So if I hadn't memoized it, if I hadn't cached it, then the time complexity was O of 2 to the power n. But then since we are caching it, we bring that to a very simple n into n. And why I'm saying n into n is because we have these two parameters that we have to care about. And since this is the only extra space that we are taking apart from the recursive stack space, since this is the only extra space that we are taking, the time, the space complexity is also O of n square in this scenario, right? So I hope you found the video helpful, and I will see you in the next one.